Welcome to session 5 of Digital Electronics Problem Solving. I am your instructor Sachin from the Indian Institute of Science. Today we'll be continuing where we left off. Last class we left at problem 3.9 in the textbook Digital Design by Morris Mano. This time we'll continue from problem 3.10. 3.10. Problem 3.10 is simplify the following Boolean functions by first finding the essential prime implicants. Part A, f of wx yz is summation 0 to 5 7 8 10 12 13 14 15. Okay, first we'll write the K-map. Wx yz we have 1 and 0 2 5 7 8 10 12 13 14 15. Those positions. This one will be covered by the quad, that quad, and that is an essential prime implicant. x prime z prime. X prime z prime is an essential prime implicant because this one and this one cannot be covered by any other group that is also a quad or a larger group. Next, this is also an essential prime implicant because this one and this one cannot be covered by any other group that is larger than that quad. So xz is an essential prime implicant. The remaining ones can be covered in different ways. You could form a quad like this, or you could form a quad like this to cover those. I'll form a quad like that, and that will give you a simplified expression for f, and the simplified expression is the f of wxyz is x prime z prime plus xz plus wx. Part B, f of abcd is summation 0 2 3 5 7 8 10 11 14 15. The K map for this has a 1 in 0th position, 2th position, 3's position. That's 5, 7, 8, 10, 11, 14, and 15. One essential prime implicant here is this, which will give you AC because it covers this one which cannot be covered by any other quad or octet. Another essential prime implicant will be this quad that is given by B prime D prime A third essential prime implicant is this pair, which is A prime BD, and the remaining one can be covered in multiple ways, so it's not an essential prime implicant. I'll cover it in that way, and that group is CD. So f of ABCD is equal to CD plus AC plus A prime BD plus B prime D prime. Part C, f of ABCD is equal to summation 1, 3, 4, 5, 10, 11, 12, 13, 14, 15. Let me move it to the next page. Then I'll copy down the structure of the K-map. Now we have to fill in the K-map with ones as 1, 3, 4, 5, 10, 11, 12, 13, 14, 15. Out of these, the essential prime implicants are that group, which is AC, and that quad, which is BC prime. Those are the essential prime implicants, and the remaining ones can be covered in multiple ways. One such way will be by forming a pair like that, which will give you f of ABCD equals AC plus BC prime plus that orange group is A prime B prime D. Part D, f of WXYZ is summation 0, 1, 4, 5, 6, 7, 9, 11, 14, and 15. Now let us fill in the K map. That's 0, 1, 4, 5, 6, 7, 9, 11, 14, 15. And the essential prime implicants are this quad, which is W prime Y prime, and this quad, which is XY, and the remaining ones can be covered in multiple ways. But the way which uses the least number of groups is by covering those ones by a pair. So that pair is Wx prime z. So now the simplified expression for f is f of Wxyz is W prime Y prime plus XY plus Wx prime z. So the essential prime implicants have used colors to mark them, and non-essential one I have just used black. I will follow that pattern for the remaining parts also. Alright, next moving on to part E. F of ABCD is summation 0, 1, 3, 7, 8, 9, 10, 13, 15. Part F, f of Wxyz is equal to summation 0, 1, 2, 4, 5, 6, 7, 10, 15. And I'll leave these two as homework. They can be solved in the same way as problem 3.10 parts A, B, C and D. Next we will go to question 3.11. Convert the following Boolean function from a sum of products form to a simplified product of sums form, and the expression is f of xyz, three variables, summation of minterms 0, 1, 2, 5, 8, 10 and 13. Okay, let's see the solution of this question. First, we'll draw the K-map. All right. Then this will be 0, 0, 0, 1, 1, 1, 1, 0. This will be 0, 0, 0, 1, 1, 1, 1, 0. And if you are filling the min terms, you'll fill ones in place of 0, 1, 2, 5, 8, 10, and 13. And the remaining will be zeros. If you want to get the product of sums expression from this, then you will have to group the zeros, and the max terms will be, if you have wx here and yz here, then 0, 0 is you're writing a product of sum expressions. In the sum of products K map, 0, 0 will be the term w prime x prime, but here it's the uncomplemented form, and instead of and you use or, so it's w plus x. So if there's a 0, then you use the uncomplemented form of the variable, so I have used w and x. And then if it's for product of sums, you will have a sum term w plus x instead of a product term wx. So the 0, 0 in wx will be represented as w plus x. So we get w plus x prime, w prime plus x prime, and w prime plus x. Similarly, y and z. This is y or z, y or z prime, y prime or z prime, y prime or z. Now you have to group the zeros. That can be done. First, you can group these 4 zeros. That's one quad. That's y prime plus z prime. Then you form another quad. So this quad is y prime plus z prime. The other quad is let me check. So this other quad is x prime plus y prime. And then the remaining zeros, wait, so actually There's another way to form a quad here that will cover more zeros. So you can form a quad like this so that these two zeros are also covered. Then that will cover these two zeros, and these two zeros are covered by the other group anyway. So this quad will be the term x prime plus z. And then only one zero is remaining, which you can group in a pair. That pair is w prime plus x plus z prime. So the function in the minimized product of sums form is f of wxyz is equal to x prime plus z or y prime plus z prime, x prime plus z and y prime plus z prime, and w prime plus x plus z prime. We'll go to problem 3.12. Simplify the following Boolean functions. Part A, f of a, b, c, d is the product of maxims 1, 3, 5, 7, 13, 15. So it's not a K-map with sum of min terms, it's a K-map with product of max terms. So this will be if AB are written on this side and CD on the other side. So be A plus B, A plus B prime, A prime plus B prime, A prime plus B, and C plus D, C plus D bar, C bar plus D bar, and C bar plus D. So you have to fill zeros in the positions 1, 3, 5, 7, 13, 15. So that's position 1, that's 3. You have to fill zeros there. And 5, 7, 13, 15. You can form two quads like that, like that. This quad is the term B prime plus D prime. This quad is the term A plus D prime. So the simplified product of sums expression is f of a b c d equals a plus d prime and b prime plus d prime. Part B, f of a b c d equals pi of 1 3 6 9 11 12 14. So if we fill a 0 in position 1, 3, and 6, 9, 11, 12, and 14, we can form one quad like that, and the quad is a prime plus d prime, and a pair to cover these two zeros. The pair is b prime plus c prime plus d, and one more group to cover the final zero, and that pair is a prime plus b prime plus d. So the simplified expression of the function is f of a b c d equals a bar plus d bar into b bar plus c bar plus d into a bar plus b bar plus d. That is problem 3.12. Next is problem 3.13. Simplify the following expressions to 1. Sum of products, and 2. Product of sums. First part, x prime z prime plus y prime z prime plus yz prime plus xy. X prime z prime is those two squares and those two squares. Y prime z prime is those four squares. yz prime, and the final term is xy, that is xy, that's also xy. So for the sum of products form, will form an octet and a quad. This octet is z prime, z bar, and this quad is xy. So the function in sum of products form is z bar plus xy. For the product of sums form, we have to group the zeros, and for that we have one quad to group those zeros and another quad to group the remaining zeros. And this quad is x prime z, this quad is y prime z. Well, these are in product of sums form, so in product of sums this will be y plus z, y plus z bar, y bar plus z bar, and y bar plus z. This will be w plus x, w plus x bar, w bar plus x bar, and w bar plus x. So in those terms, this quad will be x plus z, x plus z bar, and this quad will be y plus z bar. So the same function in product of sum form is y plus z bar into x plus z bar. And you can also verify that these two expressions are actually equivalent, because y plus z bar into x plus z bar is nothing but yx plus z bar by using the distribution of addition over multiplication. So it's just the distributive property. So those are the same expression, except that one is in sum of products form and the other is in product of sums form. That is part A. We'll go to part B. You have to do the same thing for AC D bar plus C prime D plus AB prime plus ABCD. In product of sums K map, it will be a plus b, a plus b bar, a bar plus b bar, and a bar plus b. This will be c plus d, c plus d bar, c bar plus d bar, and c bar plus d. First, we'll do the sum of products expression ACD bar. That's ACD bar. That's also ACD bar. C bar D is these four. AB bar is the bottom row. ABCD is that single one. So to form the sum of products minimum expression, we can form a quad, another quad, a third quad. You're left with three quads. First quad is C bar D, second quad is AB bar, third quad is AC. And the sum of products expression is AC plus AB bar plus C bar D. To form the product of sums expression, we have to group the zeros. So here these four can form a quad, those four can form a quad, and then there's a pair. This first quad is this quad is A plus C bar. The second quad is A plus D, and this final pair is B bar plus C plus D. So the product of sums expression is A plus C bar and A plus D and B bar plus C plus D. So to simplify into a sum of products expression, you group the ones, and to simplify into the product of sums expression, you group the zeros. But you have to also keep track of the term itself. In the sum of products term, when you group the zeros, you are forming product terms, so the variables are ANDed together, and a variable is uncomplemented if there is a 1 in that corresponding cell corresponding to that variable. Whereas in the product of sums term, each term is a sum of the variables, and a variable is uncomplemented if there's a 0 corresponding to that variable in that cell. Next problem. Part C of 3.13, a prime plus b plus d prime, a prime plus b prime plus c prime, a prime plus b prime plus c, b prime plus c plus d prime. And part D, bcd prime plus abc prime plus acd. I'll leave that as homework. and they can be solved in the same way as parts A and B. We'll go to problem 3.14. Give three possible ways to express the following Boolean function with 8 or fewer literals, and the function is a prime b c prime d plus a b prime c d plus a prime b c prime plus a c d prime. There are multiple different ways of doing this. First, let's solve this using the sum of products. We'll use the sum of product simplification and see if we can get it down to 8 literals. A prime b c prime d is that square, that cell. A b prime c d is that cell. A prime b c prime is that cell, and that cell which has already been covered. A c d prime are those two cells. There's a slight correction here. This is A prime, B prime, C prime. So this will change the K map, and the K map will be this with A prime, B prime, C prime instead of A prime, B, C prime. So let's form pairs. We can form 4 pairs like that, and F will be A bar, B bar, C bar plus A bar, B, A bar, C bar, D plus A, B bar, C plus A, C, D bar. Out of which we can take A prime, A bar, B bar, A bar, C bar common and write this as B bar plus D. We can take AC common and write this as B bar plus D bar. So this term has 4 literals. This term has 4 literals. So total 8 literals. That's one way to do it. Another way would be using the product of sums expression. Let's see if we can do it with that. You will have zeros wherever there is no 1. So there's a 0, 0, 0, 0, 0, and so this can be grouped with 1 quad, second quad, and 2 pairs. And the terms, so that's the pair covering the last group of zeros, and this will give us the expression f is equal to the squad will be a plus c bar, and this pair will be b bar plus c bar plus d bar, and this quad will be a bar plus c. This square will be b bar plus c plus d. This can again be written as, using the distributive property, c bar plus a into b bar plus d bar. This can be written as c plus a bar into b bar plus d bar. B bar plus d. So this has 4 literals. This has 4 literals. Total 8 literals. And the third way would be, we could write every single one as a min term. That would give us there are 6 min terms. F will be a bar b bar c bar d bar plus a bar b bar c bar d plus a bar b c bar d plus a b bar c d plus a b c d bar plus a b bar c d bar. That is using all the min terms. Can write this as a bar b bar. Let's see if you can do that. Into c bar d bar plus c bar d plus, right, can write this as a bar c bar into b bar d bar plus b bar d plus bd. Other term can be this will give us the same thing as the sum of products expression. So maybe we can't do that. Okay, the other way to do this would be, so in the previous product of sums expression there were multiple choices to form these pairs. So let me copy this So this pair could have been formed in a different way. Okay, so you could have formed a pair like this and formed another pair like this, and that would give us a different expression. So those quads are the same, so you'll still have a plus c bar into a bar plus c. A plus c bar and a bar plus c will still be the same. The pairs are different. So instead of b bar plus c bar plus d bar, you have this pair. That's a bar plus b bar plus d bar. Say a bar plus b bar plus d bar. And the other pair is a plus b bar plus c bar. A plus b bar plus c bar. Which we can write using distributive property as a plus c bar into b bar plus c bar. Let me check that again. It's a plus b bar plus d. So can write this as a plus c bar into b bar plus d. And the other thing can be written as a bar plus c into b bar plus d bar. So that is different from this expression, and similar to that expression you have 4 literals in the first term and 4 literals in the second term, so that gives a total of 8 literals. So those are 3 ways of expressing the Boolean function with 8 or fewer literals. So we'll go to problem 3.15. Simplify the following Boolean function capital F together with the don't care conditions D, and then express the simplified function in sum of minterms form. Part A has f of xyz is summation 01456 d of xyz is summation 237. It's a 3 variable map. So we have x on that side, yz on this side. They're asking for sum of products expression. There's a 1 and 0, 1, 4, 5, 7, 6 in those positions. 4, 5, 6, and a don't care in the remaining 3 positions. So you can form one octet including all the don't cares, and this is just 1. So f is always 1. Part B. F of ABCD is summation 068 13 14, and don't cares are 2 4 10. 0 1 3 2 4 5 7 6 8 9 11 10 12 13 15 14, with don't cares at 1 3 2 4 5 7 6 8 9 11 10. So that will let you form a quad, another quad, a pair, and this term is left as is. So the simplified expression is CD bar plus A bar D bar plus B bar C bar D bar plus A B C bar D. Give me a minute, let me check if something is wrong here. Okay, we didn't actually need so many groups, so this one and this one can be covered by the same quad, so we don't need two groups for that, but this one is left as is. So there are only three terms in the simplified expression, and the simplified expression is CD bar. That's the pink quad. The blue quad will give you B bar D bar. The single one will give you A B C bar D. So that's the simplified sum of products expression of f of ABCD with don't cares. Part C, f of ABCD is summation 5, 6, 7, 12, 14, 15. We don't care D of ABCD given by summation 3, 9, 11, 15. Part D is f of ABCD is summation 4, 12, 7 to 10, and D is ABCD. D of ABCD is 0, 6, 8. I'll leave these two problems as homework. They can be solved in the same way as parts A and B. Problem 3.16. Simplify the following functions and implement them with the two-level NAND gate circuits. I'll leave that as homework because we have solved a lot of problems on simplification, and implementing in a two-level NAND gate circuit is not very difficult. And maybe we'll see some more problems which will show you how to do that. Or let me see. I will leave the simplification part as homework. So simplify the following functions and implement them with two-level NAND gate circuits. So simplification part is homework. I will not do the simplification, but I will do the NAND implementation. So f of ABCD is A C prime D prime plus A prime C plus ABC plus A B prime C plus A prime C prime D prime. And that, when simplified, will give you f of ABCD is equal to C plus D prime. This can be written as C plus D prime complemented twice. If you complement an expression twice, then the expression will not change. Now you take the inner complement using De Morgan's theorem. This will be C prime D whole prime. You can get C prime using one AND gate and C prime D whole prime. That's the NAND gate implementation. Part B, f of ABCD is A prime B prime C prime D plus CD plus A C prime D. You can simplify that yourself and verify that the simplified expression is f of ABCD is equal to CD plus AD plus B prime D. Again, this can be written as CD plus AD plus B prime D complemented twice. And using De Morgan's theorem to take the inner complement, you get CD prime AD prime B prime D prime whole prime, and this can be implemented in a two-level circuit as follows. Have C D prime A D and B prime D as the inputs to three NAND gates. That will give you CD complement, AD complement, and B prime D complement, and then those three are fed as inputs to a 3-input NAND gate, which will give you F. So we are assuming that B prime is given to us already, and then we can use a two-level NAND gate to simplify, to implement the expression. Part C, f of ABC is a prime plus C prime plus D prime into A prime plus C prime into C prime plus D prime, which when simplified will give you f of ABC sorry, it's not ABC, it's ACD. F of ACD. This is also f of ACD, and the simplified expression will be C prime plus A prime D prime. Again, you complement it twice, C prime plus A prime D prime, complemented twice. Then use the De Morgan's law to simplify the inner complement, which will be C and A prime D prime complement the whole complement. Now you can get A prime D prime complement through one NAND gate and C times A prime D prime complement the whole complement through another NAND gate. That's the two-level implementation of the circuit. Part D, f of ABCD is A prime plus B plus D prime plus B prime C. The simplified expression f of ABCD is A prime plus B plus C plus D prime. You can get that directly without a K-map. Prime plus B prime into B plus C plus D prime, which is nothing but A prime plus B plus C plus D prime. Now again the same trick, a prime plus b plus c plus d prime whole complemented twice, which will lead to a b prime c prime d complement, and you can get that with just a single 4 input NAND gate, a b prime c prime d. You give the inputs as a b prime c prime and d. Moving on to problem 3.17. Draw a NAND logic diagram that implements the complement of the following function. F of ABCD is sigma 0123 6 7 11 6 10 11 14. First, let's simplify this expression using a K-map. The ones are filled in 0 1 0 1 2 3, or so since they want the complement, let us complement this function. If complement of ABCD is summation 4 5 7 8 9 12 13 15, and if you want to simplify that, 4 5 7 8 9 12 13 15, which can be simplified using 3 quads, so 3 terms. If complement is equal to AC prime plus BC bar plus BD, and then we have to implement this using only NAND gate, so we double complement it. Use the De Morgan's law to take the inner complement, get AC bar AC complement whole complement into BC complement whole complement into BD complement. The entire thing complemented. This can be implemented using only NAND gates by using A C complement. Whole complement is that term, and B C complement whole complement, and BD complement, the entire thing given to a 3 input NAND gate. So that's the NAND gate implementation of F. Problem 3.18. Draw a logic diagram using only two input NOR gates to implement the following function, and the function is f of abcd is a XOR b whole complement c XOR d. We have a XOR b is nothing but a XOR b complement is ab plus a bar b bar. C XOR d is cd complement plus c complement d. So if we simplify that, we'll get AB CD bar plus ABC bar D plus A bar B bar CD bar plus A bar B bar C bar D. And then we'll simplify this using a K-map. And we want it in the product of sums expression because we are doing it, we are going to implement it using only NOR gates. So since there are four terms in the sum of products expression, these are the four terms which will give 1. That means the remaining cells are all filled with zeros. So you can easily form 4 different quads and those 4 different quads will give you the simplified form of the expression f is equal to a prime plus b into a plus b prime into C plus D into C prime plus D prime. Now to get the NOR gate implementation, we can complement this twice and write it as A prime plus B whole prime plus A plus B prime whole prime plus C plus D whole prime plus C prime plus D prime whole prime, the entire thing complemented. And they're asking us to implement it using only two input NOR gates. So this NOR operation, which has four inputs, is not possible. So we have to split that into two input operations. So what you can do is write this as A prime plus B whole prime plus A plus B prime whole prime and C plus D whole prime plus C prime plus D prime whole prime complemented. So it can be done in two stages in essence. So this can be written as first you get A prime plus B whole prime from one NOR gate, then A plus B whole prime, A plus B prime whole prime from another NOR gate, then you get the sum primed with another NOR gate, then the complement of that with another NOR gate. And then C plus D with one NOR gate, C plus D whole prime, C prime plus D prime whole prime with one NOR gate, and C plus D whole prime plus C prime plus D prime whole prime can be obtained by using two NOR gates. And then these two terms are NORed again. So the implementation will look something like this. You'll have a prime plus b whole prime, then a plus b prime whole prime, then their sum primed pass through a complement an inverter. So this will be a prime plus b prime plus a plus b prime whole prime, and then you have c plus d whole prime c prime plus d prime whole prime, and the prime of those two. So that will give you c plus d whole prime plus c prime plus d prime whole prime. You take those two and pass it through a NOR gate to get f. So that's the NOR gate implementation of that function. Three point 19. Simplify the following functions and implement them with two level NOR gate circuits. F is wx prime plus y prime z prime plus w prime y prime z. So as I did in the earlier question, simplification part is homework. So I'll give you the simplified form directly. F is w plus z prime into x prime plus z prime into w prime plus x prime plus y prime, and to implement it using only NOR gates, similar to previously when we did for only NAND gate implementation. You take the complement twice, so you get w plus z prime whole prime, x prime plus z prime whole prime, w prime plus x prime plus y prime whole prime, the entire thing through a NOR gate. That is, if you give wz prime here, one NOR gate will give you x prime plus z prime whole prime, another NOR gate will give you w prime plus x prime plus y prime whole prime, and the NOR of those three will give you f. Part B, f of wxyz is equal to sigma 0, 3, 12, 15. It's homework. Part C, f of xyz equals x plus y into x plus z whole prime. This can be simplified directly. You can write this as x plus y whole prime plus x plus z whole prime. Then you can get x plus y whole prime from one NOR gate, x plus z whole prime to another NOR gate. Then you give those two as inputs to the third NOR gate, and you will get x plus y prime plus x plus z prime whole prime. Then you complement it again using one NOT gate. So you have x plus y whole prime, then you have x plus z whole prime, then you have x plus y whole prime plus x plus z whole prime, the entire thing complemented. So if you complement it again, you will get x plus y whole prime plus x plus z whole prime. Problem 20. Draw the multiple level NOR circuit for the following expression. And the expression is CD to B plus C into A plus BC bar plus DE bar. Let's call this f. F is equal to this. F complement whole complement, you complement it twice. So you get ACD to B plus C plus BC prime plus DE prime, complemented twice. Using De Morgan's theorem to complement the inner, to do the inner complement, you can write the inner complement as ACD into B plus C complement and BC complement complement and D complement complement, everything complemented. Which can be written as A prime plus C prime plus D prime plus B plus C whole prime and B prime plus C prime and D plus E prime, or actually D prime plus E, entire thing complemented. Which can again be written as A prime plus C prime plus D prime plus b plus c prime into prime plus b prime plus c whole prime plus d prime plus e whole prime, entire thing complemented twice. So you can get b plus c whole prime, then a prime plus c prime plus d prime plus b plus c whole prime complement, first you can get b prime plus c complement, and then d prime plus e complement, so that's the NOR gate implementation of the given expression. That is it for this problem solving session. We'll cover the remaining problems in chapter 3 in the next session, and then we'll move on to chapter 4.